So welcome everybody. So this is course and topics in ergodic theory. That's the official name, but the real title is Introduction to Random Walks and Groups. And as you can see, we'll meet today, Tuesday from 10 to 12, and Thursday from 10 to 11. Let me know if there's any issues with the audio or video since we just started. So hopefully also the people online can see the board fine. Okay. And so, by the way, yeah, so my name is Giulio. Spelled like that. Remember the spelling. Most people get it wrong. The U is after the I. There's no J. There is the I, though. It's not Giulio, it's not Guido, it's not Giulio. Something like this. Anyways, and so this is my address if you need to reach me. And so I'm a associate professor at U of T, and I work in dynamics, ergodic theory, and definitely random walks and groups is one of my specialties. So if you have other questions outside the class, I'm welcome to answer them if I can. And so as you all know, this is shared with the Fields Institute that is very kind to host us. So this is both the Fields Academy course and also is a U of T graduate course. So I think at least all of you, at least the people that intend to take the course seriously, they should enroll in either through the Fields portal or through the U of T portal. I was told that everybody should enroll in the Fields one, but I'll double check with the administrators about that. Okay, anyways, this is all the bureaucratic part. And any questions about the logistics? So sometimes it might be that 1 or 2 times I will not be here, so I will just do it online. So I'll let you know, but it will be at the same time. But most of the time. Okay, very good. So what is this course about? As you can tell, it's about random walks on groups. So there are 2 fields of mathematics that meet each other, and actually probably more than 2. So when I say random walks, what do you think? What field is that? Probability. That sounds legit. And when I say groups, algebra. Yes, indeed. So of course, part of the whole gist is to study some stochastic processes, some random processes on groups, so on objects that have an algebraic structure. And of course, the interaction between the probabilistic behavior and the algebraic behavior is always something we are meaning to understand. And there's also 2 other fields of math that are involved, even though they're not completely in the name. Well, one is maybe hinted at here, ergodic theory. So ergodic theory is the study of measurable dynamical systems. So dynamical systems from a point of view of measure and probability. So definitely this has to do with dynamics. And then there is another field that some people here study, that is geometry. Yeah, geometric group theory if you want to be more precise, but let's say geometry. So in fact, the way, I'm not an algebraist at all, but maybe one could say that I'm a bit of a geometer. So in fact, the way you know, the probability and the algebra interact, so these groups that we have here will not be just groups, abstract groups, but there will mostly be groups that act on some geometric space. So the space of isometries of a manifold, for instance. So there is geometry involved. And so in fact, what I find really beautiful about this subject is the interaction, you know, between the probability and dynamics. So something that happens on some process that you can define on your space and the geometry of the underlying space. And of course, the algebra and the geometry also famously are related. So certain types of geometries are related to certain type of algebraic structure. For instance, whether the group is abelian or not, you can sort of see it in the random walks and stuff. Okay, so this is just very, very broad strokes. Okay, so let's start a bit more, in depth. So the whole field, of course, is kind of old, but there is a sort of turning point, which is due to Furstenberg. So I think the first name that you should remember that sort of started the whole story of random walks and groups is Furstenberg, that wrote this paper that is called Non-Commuting Random Products in the 60s, I think. And we will see exactly what is the kind of thing that he was meaning to do. And in fact, this is indeed the object that you're going to study. You can, another way to say random walk and group, you could say it's a non-commuting random product. So again, so what is the classical probability? So probably you know some theorems in classical probability. What's an example of a theorem in probability that you've studied? Tomer.
Linearity of expectation.
Yes, that's a lemma. Yeah. What about more of a theorem? Yes. Central limit theorem, probably the most famous. Yes, exactly. So in general, what is the setting of classical probability? Well, the setting of classical probability, you have a sequence xn of random variables. So sequence of, and usually in a very, very classical setting is maybe independent and identically distributed random variables. So if you're not super familiar, we'll go deeper in the technicalities, but I'm sure you heard of this for sure. So you have such random variables. So basically, I don't know, for instance, xn is 0 if you toss a coin and you get head, and 1 if you get tail. That's the most famous example. And then what do you do? Well, for instance, you have the law of large numbers even before the the central limit theorem. You have the law of large numbers, which says the following, that almost surely, so meaning that with probability 1, well, if you take the sum, okay, now we need some condition, and here, for instance, we can assume that the expected value of norm of x1 is finite, and we can call this L some number. So if you take this sum and you divide by n, so you take an average, then almost surely this average converges to a number, which in fact it's the same L. Well, actually, you don't want to take the absolute value if you take the sum. So yeah. Anyways, so and yeah, so this is of course very famous type of limit theorem. So in probability, we're interested in the asymptotics of processes that are defined at each stage doing some random operation. And of course, so the other one, which is even more famous, is the central limit theorem. And it says not almost surely, but different type of convergence, which is if in addition, if moreover, well, not just the first moment is finite, but the variance, so your sigma square is the variance of xi is finite, then you have a even sort of, so to speak, stronger result that you see this average is approximately L. But if you normalize it correctly, you can also tell a bit more precisely how different these two things are. And in fact, the way you would do it is like this. You do x1 plus xn over n minus L. So this is sort of the difference And now we want to amplify this, so we multiply by square root of n. So this is a new random variable, and this one converges weakly or converges in distribution to a normal distribution with variance 0 and with mean 0 and variance sigma squared. Again, it's not so important if you don't know the details, but you see that after renormalizing this process, you get some very nice random variable, which is in fact sort of universal, which is the miracle of the central limit theorem. So what does in distribution mean? Well, again, most of you probably know, but maybe let's do even more concretely. More concretely is if you fix A and B, so with two numbers A and B, you look at the probability that that guy there is in the interval from A to B. Well, this converges to a precise number as n goes to infinity, and this is the integral of the Gaussian distribution between A and B. So it's 1 over square root of 2 pi sigma. Let's say sigma is non-zero and you get this scary formula. But okay. So we understand very, very well what is the limiting process of when you average random variables. Okay, so this is sort of well known, but what is the point of view of Furstenberg and in the general the theory? You see this non-commuting. So you can interpret, you can think of classical probability as, you know, that you're looking at random variables that have real values. So these are real valued random variables. So the outcome xn is a real number, and of course you could also make it into RD if you want a multivariate distribution. Means just that this is just a d-tuple of values, so it's vector in RD. That's also a slight improvement, but not different in paradigm. And so of course, so this can be thought of as a random walk on R, which is a group with the addition operation. So here we take random variables and we add them, and we want to find some limit law. But so in the random walks and groups situation, well, what we do is we extend this and we replace this abelian group R with any other group in principle. So the idea is you replace R by a group G. And G in principle could be any group. Then the groups that we like are many, but for instance, historically the products that Furstenberg was referring to were matrices, products of matrices. So for instance, G could be SL to R or SL and R. And in the end, eventually we will see more complicated groups. For instance, G would be the group of isometries of certain manifold X. X, for instance, it could be the hyperbolic plane or hyperbolic space, or it could be even some manifold of negative curvature, or it could be even more complicated, a graph or something. So it could be, so X could be a manifold, X could be a graph, and then again, if you're into geometry and topology, well, you like other types of groups, like you like the mapping class group, you like relatively hyperbolic groups, So these are also type of groups that you can put in this setting. So depending on, so in fact, so the theory of random walks of groups started as theory of on Lie groups, so on groups that are groups of matrices, and this had all this huge advances. And then most recently, this was somewhat imported in geometric group theory. So then you look at groups that are isometries of some graphs or complex or things like this. So this is a very, very broad setting. Yeah, maybe it's a good time to ask if there's questions, curiosities, or comments. Okay, so what are examples? So let's look at some examples. So wait. Huh. Okay, so the first example is the one that we already know, is the classic simple random walk on a grid, and this can be RW will be always random walk, and this also, even though it's more classical, so to speak, can be definitely cast into the context of random walks on groups. Because what is the group here? Well, the group here is Z to the D. Here's the dimension. And you can take, in fact, and you can think of G as a group is acting on itself. So in general, we use the following notation, which is very useful. So a group action of a group G on a metric space X with some metric D, well, is a homomorphism as groups rho from the group into the group of isometries of X. So, of course, the group of isometries is just the group of maps from X to X, such that, well, certainly distance between f of X, f of Y equals the distance between X and Y for every X and Y. Now, there is a little bit of an issue if the space where we are looking at is really complicated, like it's an infinite dimension in some way. So maybe it's better to also assume that F is bijective, just to avoid issues at this moment. But then, yeah, depending on the situation, you can slightly relax this. But so clearly, this is a group. So G, you can think of G as an abstract group, and it acts on some space. And so, and however, we will forget the notation. So the notation will always be that if you take O is a point in X, we'll just define, we'll call it GO, or G dot O is, of course, will be a rho technically is rho of G, which is an isometry on O. But we don't want to write that, we just write the G. Okay. So if you have the group, say the group of integers or powers ZD, then, well, X act on a d-dimensional grid, the dimensional square grid. So how does it act? Well, by translation, right? because if we have, right, so if we have O is, right, so if G in G, well, we can call G as T1 TD, and O is in X, so well, O is X1 XD. Well, we can obviously define just the action by translation. So this is the definition, and in this situation, we define GO is X1 plus T1 XD plus TD. So this seems like a convoluted way to say what we already know, that the group of integers acts on a grid by translation. So the first sub-example, if D equals 1, well, then X is just really a classic one-dimensional lattice, X. And then how do we define a random walk on, and we have a base point, let's say that our base point is O, which is 0. If we identify X with that, and then, well, how do we define a random walk? Well, we have to put a measure on this group, and the way we do it is the following. So we let mu be, for instance, the measure that is 1/2 the delta mass at +1 plus delta mass at -1. So what does it mean? So this is a measure, it's probability measure on G, and G is Z for us. And so what does this mean? It means that the step of the walk is you go to the right with probability 1/2, and you go back. So you go to -1 with probability 1/2. So that's where this 1/2 comes from. And so this one, so in this case, you can define the classical random walk by saying that it is the random walk on Z generated by this measure. So in general, the general setup is the following. We consider a group G. We consider a measure mu. Mu is a probability measure. And then what do? We draw a sequence, which should denote Gn of elements of G with law mu. And these elements are independent. So these are independent of each other. So what does it mean in this case? In this case, it's like, okay, I can take, I draw the first G1. It could be either 1 or -1 with probability 1/2. I do coin toss. And then I do another one. So I have G2, which is also independent of the previous one. So I put the coin back in the urn, and I toss it again. And so I get either plus or -1 with probability 1/2. And so forth. And what I can do is I can compose them. So I can multiply them in the group operation. So in this case, the group operation here would be plus. In general, if you have a group, you call it like that. You just write in multiplicative notation. And what we care about is the product. This is non-commuting random product. So it's Wn. So we define Wn is this product. And this is, so Wn, the sequence Wn is called a sample path of the random walk. And so the most important question is, what is the behavior of this? So this is also a random sequence because the choice of G1, G2, Gn was done random. So in this case, when you have the square grid, for instance, so in the square grid for G equals ZD, you see, what we called it before x1, xn, now we call it G1, Gn. It's just the same thing. So before we call it x1 plus x2 plus xn, and the say the central limit theorem. And here now, so now we just call it G1, G2, Gn. So, but it's the same thing. It's just a change of notation. It's because now the group operation is just group composition, and not this. A summation is, of course, the group operation in this special case. Okay. So, right. And so, and what else? So what is Wn? Well, if you take Sn is the sum, which was the thing that you studied in, say, the central limit theorem, well, in this case, you get the product, so it's Wn. Okay, so making sense? Let's say this is just notation, but one has to get used to the notation. So far we have a group, we have a measure, and so then this data of these two things gives us a sequence of elements, which are called increments. I will write more precisely. And then we have the sequence Wn, which are called the sample paths. So also the important things to note is that the Wn are not IID. So this xn's are the increments, so those are independent, but then when you take Sn, these are not IID. Yes.
You said that the product for Wn was not commutative.
Yeah.
I think so. That's in general, but in this example,
right. So if we do the group ZD, of course, the group is commutative, so the product is also commutative, of course. But in general, indeed, it's important to decide whether you multiply on the right, like we always will do. You could also multiply on the left. It has other advantages and disadvantages, but in general, yes. Other questions? Yeah. That's a good question. So it depends on what class of group. A priori, this process is defined. There's two classes of groups that people study most often. One is just discrete groups, or countable groups. So then mu is just a measure on a countable set. So there is no issue with the topology. The other issue is G could be a Lie group or locally compact group. And then mu, yeah, then there is some certain compatibility maybe between that and the Haar measure, depending on what kind of thing you want to look at. Yes. Yeah. But in this class, mostly we will focus on countable groups. So in fact, it will not really matter. Yes. Okay, so in the example, so what kind of properties are we looking at, right? Right. So what are the questions that ask about the behavior of this WN. So in general, one thing you could say, oh yeah, before that, let's maybe also introduce the group action. So if again there is a group action, there is a group action. So G has a map into the isometries of certain space. Then one is interested in not just the random walk on G, but what happens to this geometric space on which G is acting. And so what we do is we fix some base point O in the space, and we look at W, this random group element W, and how it acts on this space point. And this sequence is a sequence in the space. So it has other advantages. For instance, it has a metric, and so you can look at distances between these points and things like this. And it's slightly annoying, unfortunately, that the way the thing is set up is not so intuitive because of the way you multiply on the left and on the right. So okay, so let me give first an example. So in this ZD example, in the grid example, well, in the grid example, well, we can take O to be just the 0 vector, for instance. That would be the most obvious thing to do. So if you are in a, say, two-dimensional grid where you have your starting point, and then maybe here you have that. So here what happens, so in the one-dimensional grid, well, the first step is either left and right, so left or right. So maybe let's say that W10 is here. And then the next step maybe is again right. So maybe this is W20. And then maybe the third step is going to the left. So you get this, and maybe you get that, and that, and that. I don't know. Every time you can do all sorts of things. And we are interested in this type of movement along the line. So this would be an answer. And here in the two-dimensional grid, it's kind of the same. So what you could do, the measure that you could pick, well, there are many measures you could pick. The most famous would be to take the 4 neighbors and just go there with this uniform probability. So there are 4 options. So you could say so 1/4, and then you can go to either 0 plus 1, or 0 minus 1, or plus 1 0, or minus 1 0. So this would correspond to the classical random walk on the grid, where you have 4 directions for the first step, and then again, once you pick one, well, maybe the second step is again one of these 4 directions, and so forth. And so you're doing your walk like that. So this is W1 0, W2 0, W4, and so forth. So these are all well-known examples, but there are other examples where you see that the geometry will be different. And as I said, part of the question is, how is the geometry of the space influencing the nature of the process, like the dynamics of the process? So here's another case. So suppose that G is a 4-valent tree. So X is a 4-valent tree. Okay. So our space looks like that. It has every vertex has 3 edges. Sorry, has 4 edges. That. And then you also fix base point here. And now you can also have a similar probability. So G could be, for instance, the group of isometries of X as a graph, right? So this is a graph. So there is a distance, which is the distance in the graph. And so here we can call A the operation of going, everything goes up, and A inverse would be the operation of going down, and then B going to the right, and B inverse going to the left. So like sort of moving the whole tree. And if you do that, well, you can also define a measure, which is 1/4 delta A plus delta A inverse plus delta B plus delta B inverse. And this type of measure induces a walk on this tree, right? And what is the walk? Well, the walk goes up and right and up, and you can backtrack and do various things. But it turns out, and we will see pretty shortly, that in this case, the walk will behave very differently from the walk on the square grid. Even though, in a sense, they're kind of similar, there is this fourfold sort of symmetry. And in this case, you take a uniform measure. And here also you take a somewhat uniform measure. But you see that the tree has different geometry from the grid. What's the main difference? Yeah, exactly. So here, the paths could close. While here, well, the paths cannot really close. You can backtrack only if you retrack the whole path. Right? And yes, and so it turns out that there are many differences between these two examples, and we will see them later. But let me just say that on a two-dimensional grid, the random walk is recurrent, and also the speed is 0. So meaning that the random walk will almost surely come back to the origin infinitely many times. While on this tree-like structure, the random walk is transient, meaning that the probability that the walk comes back to 0 infinitely many times is 0. So in fact, the walk will tend to sort of diverge somewhere. And moreover, what happens here is that the speed of the walk will be positive.
How do you speed?
Just, you look at the distance after time n, distance over time. We will define everything, but yeah, just the distance over time. It turns out, and we will prove it shortly, that if you look at the distance after n steps, over time, this will convert to a positive number. Rather here, it turns out that the walk is recurring, and so yeah, in fact, the speed, if it exists, it has to be 0, because after a million steps, you are progressing distance 0, so that has to be 0. So you see that, and what is difference between these two situations? Let me just say it. So in this situation, you have a flat geometry. So this lives in the Euclidean plane. There is no curvature. So here's the geometry. And in this case, well, it turns out that this has hyperbolic geometry. Then to make this precise, we have to define many things, Gromov hyperbolicity and so forth. But in a way, here, you can in fact replace this object with X to be the hyperbolic plane, the Poincaré upper half plane. And G could be the group of isometries of that. which, as you might know, this is PSL2R, a group of 2 by 2 matrices. And you can do a similar thing there. And in that case, you're either upper half plane model or in the disk model. Well, what happens is pretty similar, that if you start at the point 0 and you run your walk, so you have W1 0, W2 0, W3 0, and so forth. So your walk, in fact, will not come back to 0 almost surely. And in fact, it will converge to some boundary point. So it will pick some direction. So here the geometry is hyperbolic. The group is non-abelian, and the curvature, well, you cannot really, it's hard to measure the curvature in a graph, but in a hyperbolic plane, we know the curvature is negative. So the curvature here is negative. And so part of the goal of the course is to really explain what is the difference between, this type of random walks, where you see that there is, on the one hand, the difference in the dynamics in what the random walk does, and the other thing is there's difference in the geometry, what the space looks like. And these two spaces clearly look different, and how do they look different, and what's the way to make this precise? Okay, maybe are there any questions, comments? Yeah, I think. Okay, so again, so now let's delve a little bit deeper and start to asking what are indeed the precise questions that we can ask. So the first question that people ask in random walks is the recurrence versus transience question. So let's make a list of questions. So the first one is, so you start with a group. In general, the setting is always going to be a group, a measure, and then there will be a metric space. So XD will be a metric space with some metric. So this is the type of setting. And then, and we will fix some base point O. It's usually not very important what the base point is. Okay, so the first question is the recurrence versus transit. So let's say the following definition. So if X, let's say that F is a graph for simplicity, because otherwise it's a bit trickier to define what it is. We say a random walk is recurrent if, well, the probability that the end step of the walk equals the base point infinitely often. So for infinitely many values of n is 1. So this seems a very strong property, but it is true for certain walks. So otherwise, the random walk is called transit. In fact, so the main theorem that the first classical theorem that was studied is the following. So the famous theorem of Polya, that the simple random walk so what is a simple random walk? A simple random walk means that at each stage you're choosing only the neighboring vertices. with uniform probability, like we did here. We had 4 neighbors, so we choose them uniformly. On ZD is recurrent if and only if D equals 1 or 2. So here you already see a very, very nice geometric property that you can tell the dimension of the space by looking at the behavior of the random walk. So in fact, yeah, in the words of the famous joke by Kakutani, if you have, you know, a drunk person on in a 2-dimensional city, you know, even if it's drunk and is walking randomly, it will eventually go back home. But a random bird will be lost forever, because in 3 dimensions, the random walk will be transient. So the probability of coming home is 0. Okay, so this theorem is only on abelian groups, but it's very important. So I think we will give at least a proof of the case D equals 1, 2, and 3 to see what is the difference. But I think now it's a good time to take a break. So yeah, so let's take 10-minute break. So we'll resume at 11. Of course, it's a good time to ask questions if you have them.
Yeah, the speed quantity. So it's
Right.
It's positive, but it's not telling you if you're picking up a particular direction or not. That it could be rotating.
No, I just mean the distance between the first point and the end step.
Right. Right. So in practice, so in principle, you could be like going in so many different directions. And
Yeah.
So is there a quantity that tells you whether you actually have a?
Yes.
Okay.
I mean, this is related very closely to the geodesic tracking that we will talk about later, right? Because a way to say that you're picking a particular direction is you can say that there is a geodesic in the space, and the walk is close to this geodesic and is making progress, but along this geodesic. So that's the next step. Yeah. Absolutely. So this again will come. Yeah, exactly. So this is indeed what we were going to study, that in these hyperbolic situations, the random walk will converge to the boundary, then you define a hidden measure. And then you can study properties of this hidden measure. Yeah, that's exactly right. So mu could be anything. One popular choice, if you have a finitely generated group, is to take it supported in a generating set. But a priori, you could define, you see, mu of k equals 1 over k squared for every k in Z. And that would be good, except the total mass would be pi squared over 6. So you have to normalize that. but yeah, so you could have a measure that does, makes infinite, unbounded steps. This is still a walk. And in fact, this is something that I studied a lot. Like this is how to generalize from finite support to more general measures. Yes. Any questions from the online audience? Yeah, that's a good question. So yeah, so there was a syllabus, but also more importantly, there are lecture notes that I started. I mean, I have most of them already, but I uploaded the first 2 chapters on the fields portal, the equivalence of Quarkus. But then I can also maybe post it just on my website. Maybe that's the easiest. Yes. And then and there will be some assignments. Yeah. So I think this is part of the deal of this course, that there has to be a few, and then there will be the most important thing will be final project that will happen at the end. That's for sure. So I can talk about I should talk about the logistics. Maybe let's wait a couple more minutes to make sure that everybody's here. Yeah.
What would you say are prerequisites for this?
Yeah, I think so. yeah, I mean, a bit of measure theory and probability, I think, would be useful. I mean, but not too much probability, but a bit, and then something about groups and group actions, and bit of topology, metric spaces, something like this. It is fairly self-contained, but the problem with all this type of topics is that there are various fields of math that come together. So maybe from each individual one, we don't require a ton, but then you have to go a bit across. Yeah. Other questions? Okay, actually. Okay, I guess we can restart. So okay, let me just briefly comment on the logistics. First of all, I think we can start at 10 sharp, which appears to be the Fields tradition, and most of you were here anyways at 10 or 10:02, so I think we can aim for that. Okay, in terms of grades and assessment, if you need some, so there will be some assignments, not too many, also because as a course becomes more advanced, it becomes harder, of course, to give reasonable assignments. But for the ergodic theory part and beginning probability, I think it's good. There will be maybe 3 assignments, something like this. Yeah. Okay, and then the most important part of the grade will be determined by a final project. And as I've done many times before, yeah, so you can pick the topic, or I will suggest some topics. If you really care about some topic, you can just suggest, or otherwise I can suggest. And there will be two phases. There will be oral presentation at the end of class, some point in December, and then you will have to write things up. So there will be like a short write-up, maybe, I don't know, 8 maximum 10 pages, something like this. So you have to write a report, reading some paper, and try to report. Okay, and I guess the most important, most of the topics will be dealt with from the lecture notes that I started 5 years ago, and then the first time I taught this course, and then the second time when someone else was already taken it. So yeah, so this been revised a few times, and hopefully they're getting towards a good form. So anyways, I put the beginning part of them already on the LMS portal, which is the one the fields use. Maybe I just put them also on my website, which makes it easier for everyone. And as it keeps going, they will grow. So recently there are two sort of books that I think are kind of nice. So if you're interested, so this recent book by Steve Lally that just came out like last year, which is Random Walks and Infinite Groups, which is indeed what we're talking about. I haven't really looked at it in detail, but the topics definitely match the topics that we're interested in. And there's this guy, Ariel Riyadin, who has a lot of lecture notes, very nice lecture notes, in particular this one on harmonic functions and random walks and groups. It's basically a book, and I think it's on this guy's website. So these are some options. There are older books, but yeah, somehow they're not, I think, as don't have the flavor that we're going for, which would be not just probability, but intersection between probability and geometry and topology. Any questions about the logistical part? Okay, so forgetting about that, so let's keep looking at the list of questions that we are each interested in, not just transience and recurrence, of course, is the first dichotomy. The second object is the one that we mentioned, which is the speed or drift of the random walk. So definition is usually we call it drift, or sometimes we can just call it speed of the random walk, is the following quantity, which we indicate with L, which is the limit as n goes to infinity of the distance in this famous metric space between the base point and the end step of the walk divided by n. So again, this is distance divided by time, so it makes sense. There is the speed. Now the question is, does this limit exist? Well, it turns out that under pretty mild condition of finite first moment, this limit exists almost surely, and it's almost surely independent of the specific path that you. So we will discuss that later, but if this exists, we call this the drift or speed. In fact, computing explicitly this number is quite hard in general, one of the hardest problems, in fact. But what we can tell at least is whether this is 0 or it's a positive number. That already is quite interesting information. So here's the question. Second question is the drift L positive? Yes.
When it's positive,
Mhm.
like you have to something. Is it often positive? Is it often like bounded away from 0 independently of the numerator of a measure on this loop, or
No, very rarely so. I mean, you can take a very well. Again, it depends. If there is some discreteness assumption, you see. I mean, in principle, you could move very, very little. Now, if you are if you have like a lattice in SL2R or something like this, well, the discreteness. So if you give up the discreteness, clearly L can get very, very small. Now, if you have a discrete lattice, then the discreteness kind of tells you that you can't really do two small steps. But it's really tricky to find lower bounds on this guy. So yeah, and so as you said, so as an example, and now we will see, as you're saying that a simple random walk on ZD has drift 0 for every D. So this is independent of the dimension. So you see already the difference between dimension 1 and 2 and dimension 3. So in dimension 3, the walk is indeed escaping to infinity in some sense. It's not recurrent. But on the other hand, very slowly. The speed is still 0. So after n steps, if you look at this, and this is somewhat, for instance, this is you can prove that, for instance, using the central limit theorem, or also you don't, maybe you can do it much in an easier way. So this maybe could be good, actually a good exercise. So but a simple random walk on a tree, on a 4-valent tree, has positive drift. And in fact, if this we can look at it. Why? So
why was something in between important?
These are hard questions. I mean, yeah. So if there is even weak hyperbolicity, this is one of our theorems that eventually L will be positive. But there has to be certain, like for instance, 2 independent loxodromic or something like this. That's definitely enough. But then, yeah, in general, it's always hard. You have abelian groups are like the most flat, of course, and then the free groups are the most hyperbolic. And then in the middle, there is this big sea of complicated things, and it is some like groups of intermediate growth and stuff like this. So this is becomes interesting. Yes. Right. Well, you get infinites because you see the central limit theorem basically tells you that the distance after n steps is roughly square root of n. So that's why if you divide by n, you get 0. So you have to divide by square root of n to get something. So let's look at a 4-valent tree, which I think is a bit less common in a standard probability course is so in fact, for the simple random walk, we can prove ourselves easily that the drift would be positive. And what's the reasoning? Okay, you start at the origin again, and we look at the nth step of the walk. So where is it? Well, it's somewhere like here. This would be Wm. And we define the following random variable, dn, which will be the expectation of the distance. Sorry, just not the expectation, just the distance between the origin and the end step. So just literally this distance is the end. Okay. And now, what do we know about this this distance? What about the next step? Suppose I am at this point at distance say 2 from the origin. What do we know about the next step, right? So what is dn plus 1? Yeah. Yeah, that's exactly right. So you could be bigger by 1, and that has probability 3/4. Or it could be smaller by 1, and that's with probability 1/4. So this is the unbalance that makes it somewhat easily tell the property of the drift. So let's think about it, because dn plus 1 is dn plus 1 with probability 3/4, and it's dn minus 1 with probability 1/4. Well, I'm slightly cheating here. There is one case that I haven't discussed, right? Yeah, if it happens to be 0 to begin with, then, well, it's even better, because you can only go up. You're at the bottom. This is a good thing. When everything goes wrong in life, you can go only up. So that's the thing. So here, yeah. So in fact, if you really want to be precise, well, this is like bigger than that. Like, yeah, sort of, yeah. With probability 1/4, it's either, yeah, it's even bigger if you want to be. So in the end, what happens? You see, if you take dn plus 1 minus dn, what is the expectation of this? This is bigger. Well, if life is good for you, with 3/4 probability, you are advancing by 1. And if life is bad for you, but just only with probability 1/4, well, you're going back. So it's minus 1.
Why is it bigger than or equal to that?
Yeah, because whenever in the kind of rare case that dn is 0, then you can only go forward. Yeah. So technically, it's like that. Yeah. Okay. So that's, of course, this is 1/2. So on average, right? 1/2 of the time, you're making the progress. So this, of course, if you telescope this series, you would get that the expectation of dn is bigger than n/2. Right? Maybe n minus 1. Okay, I think that's fine. Yeah. So if there is a limit, which again is a lemma that we will see next, but let's use that for the moment. The expectation of dn over n is bigger than 1/2. And so this one converges to the drift, which is so bigger. So we're only using the fact that the limit exists, which again we will prove maybe next time. So it's not that complicated. But the idea, of course, is that on average, after n steps, you're doing at least n over 2. After n times, you're doing n over 2 distance. Is it sharp? What do you think? Yeah, so here's the exercise. Prove that indeed L equals 1/2. So indeed, yeah, and I mean, the idea is basically that indeed it's very rare to come back to 0. So even if that might get you a little bit above 1/2, since it's pretty rare to come back to 0, then indeed on average your progress is only 1. Okay. And the other exercise is, what about a q-valent tree? Instead of, so here is q equals 4. What about other q's? I guess this one maybe we can guess. What would that be? Q minus 2 divided by, let's see, what's the argument, right? So in this case, you would have q over q plus 1. Sorry. You would have q minus 1 over q, possibilities of going plus 1, right? And then you're going to have 1 over q, possibility of going to minus 1. Right? Yeah. And so, yeah, I think you're right. So this is q minus 2 over q. And again, to prove that it's really L takes us slightly more work. So the strange thing here is the walk, the measure is somewhat symmetric here. So we have not specified the direction. But what does it mean to be transient? It means that almost surely at some point the walk will decide. For instance, suppose you have these 4 choices. You can go north, south, east, or west. Right? At some point, since you're almost surely you're gonna be in 0 only finitely many times. Right? So it means that after 273 days, you will not go back to 0. So it means that you have to be in the complement of this area. The complement of this area is disconnected. There's 4 choices. So this means that after 273 days, you're in one of the 4 islands. And they removed the bridge between the islands. So you're going to be stuck on, say, this island forever. Now you can apply the same process again. Right? You look at the first point on the island and you say, okay, at some point you're going to leave that. After 5,000 days, you're going to leave that for good. And so again, you will remove this bridge, and you have to make another choice, either here, or here, or here. And the same keeps applying. So you see what happens to this random walk on the tree. You see that almost surely, eventually, you have to choose a sequence of these smaller and smaller sets where you're going to stay there forever. So this means that you're going to converge to the boundary of this tree. You see what I'm saying? So let's make this precise, and also let's so the third question is, does the random walk converge almost surely to a suitable boundary, which depends on the context, boundary which we denote by boundary of x. So again, this is slightly dependent on the context. What is the boundary? But clear in the tree, I think it's kind of clear what it means. So for instance, if we have a 4-valent tree, what is the boundary of a 4-valent tree? Anyone who's not in geometric group theory? Yes? Yeah, it's infinite sequence. It's like, in this case, what we could say, we can say that the boundary of x is infinite geodesic rays based at 0, for instance. This is a good description for a tree. What does geodesic ray means? It means you keep going further and further from the origin forever, right? So here's the picture again. And here, you start at the origin and you're going, say, in this direction. Geodesic means it's length minimizing, so you cannot backtrack, otherwise it's not geodesic. So okay, you pick, say, this one. And then I have to pick, say, this one. And then I pick this one, and so forth. Also, combinatorially, if we remember this way of labeling things like A inverse, B inverse, so forth. So here we have B inverse, and A, and so forth. So if we label this corresponds to infinite words in this alphabet. Infinite. The key word is reduced words in alphabet. And the alphabet here is just A, B, A inverse, B inverse. So what does reduce means? It means that there is no obvious backtracking. So if you do A, you don't immediately do A inverse. And if you do B, you don't immediately do B. Of course, if you know about free group, this is exactly what a geodesic path in the Cayley graph of the free group is. So we will, of course, define that too. So a word W is, I don't know, S1 SK is reduced if Sj is different from Sj inverse for every j. Sorry, j plus 1 inverse minus 1. Yeah, it's fine for every j from, say, 1 to k minus 1. So this corresponds, and so this corresponds to the no backtracking. And so, in fact, the proposition, and we're going to see a much more subtle versions of that for almost surely, a simple random walk on the, say, q-valent tree, because it's the same. Instead of having an alphabet of like that, you can have a slightly different alphabet, but it's the same. Q-valent tree converges to a point on the boundary of the tree. Again, in this case, you could say something like this. You can say combinatorially that, let's say that for every n, for every k, there exists an n, such that for every n bigger than n, if you look at Wn, well, Wn starts with a fixed prefix. So the prefix of this word is stabilized. I guess in the, well, either in the geometry, yeah, okay, well, to say it a bit, yeah, you have to, yeah, not as a path, but as a geodesic. So maybe we can say the following, that there exists an infinite word. So let's say the following, that there exists an infinite reduced word Sn, so S1, S2, S3, S4, such that again, for every k exists an n, such that for every n bigger than n, the geodesic representative of Wn, so yeah, the of Wn starts with S1 Sk. So why do I need to say geodesic representative? Because the walk itself can backtrack. But what it cannot do is at some point this Wn, this path could be weird. But if you look at the associated geodesy from the endpoint to the starting point, well, this starts with S1, S2. So it's like saying that Wn is always in this area from some point on. Yeah. Yeah, of course, in greater generality, we can say it more geometrically, but in this case, we can just say it's combinatorial. Okay, so what else? So yeah, so in general, so whenever you have, and so another theorem, so another theorem that we're looking at, case of this context will be whenever you have a group, say, acting on a hyperbolic plane. So for instance, there is this famous theorem, let's say, that we will discuss in this class of Furstenberg. That the same is true if you look at the action of, say, SL2R on the disk. So for any non-elementary measure, which we will define, mu on SL2R which we think of the isometry group of the hyperbolic plane. So maybe to say, yeah, then let's say PSL2R to say that this is precisely the orientation preserved isometry groups. For any base point, almost surely indeed the limit as n goes to infinity of the random walk, which we can call psi, exists and lies in the boundary of the disk. So this from the tree can be extended, for instance, to groups of 2 by 2 matrices and to many other things. Right, so the picture is the picture that we just said before. So you start with O. So here's the boundary of H2. In this case, is a circle. And so what happens is that, yeah, you take PSL2R. Again, PSL2R is a group of isometries. So it's a group of 2 by 2 matrices A, B, C, D, such that A, B, C, D are real. Determinant is 1, and then we quotient by plus or minus identity. And of course, so this group acts on the hyperbolic plane, and the easiest is to look at it in the upper half plane model. So if H2 is Z in C, such that the imaginary part of Z is positive, then we just say that A, B, C, D acts on the point Z as Möbius transformation, AZ plus B over CZ plus D. Now for symmetry, it's a bit better to draw it in the disk model instead of the upper half plane model, but it's the same. And so what happens is that almost surely whenever you pick a measure on this group, you look at the trajectories of this walk. You have W1 0, W2 0, W3 0, and so forth, Wn 0, and it happens that indeed this walk can do various complicated things a priori, but eventually it will converge to some point, and this point will be on the boundary. So this is the analog of what we said about the tree in this other situation, which is manifold of negative curvature. And in fact, I proved a much more general version of this a few years ago, and we will discuss that later in the course for any hyperbolic metric space, but this is a good intuition. Any questions so far?
Does the limit exist in here? You said this. Does it imply the speed is positive or not necessarily?
Not that I know of. I mean, yeah. Not that I know of. I mean, in general, in this space, both things are true at the same time. For non-elementary, but the speed is positive. Yeah. Yeah, I don't think formally it does. Yeah. Other questions?
For
yeah.
example, in R3, do we know that you don't convert at particular points? You know, like you keep the paper or something? Or...
Right. Yeah. So in R3, yeah, there is no way. Yeah, there is no sensible way to define a boundary unless, except for just a point, so that you converge. Yeah, that's right. Right. So yeah. So okay. So once we have this, so the next thing we can do is we can define the hidden measure. And so what is the hidden measure? Well, is indeed the probability that the walk converges to certain subset. So if I know that almost surely it converges to some boundary, now I pick a subset of that, like say A, and I want to know what is the probability that it ends up in the yellow part as opposed to the humble. So we define we call it nu mu because it depends on mu. So nu mu of A the nu mu is a probability on the boundary. Again, depending on which particular boundary, you always do something like this. And so what is nu mu is the probability that the limit of the sample path converges to a point in A. And the hidden measure is also called sometimes harmonic measure. So a harmonic measure is a measure that is not invariant, but it's invariant on average. So nu is harmonic measure because, so in this case it is, if, well, what happens is the following. You take your measure. On the other hand, you have a group acting on this boundary. So you can push forward the measure by the group action. So G is a group element, so it acts on the boundary. For instance, the group of Möbius transformations acts on the circle by homeomorphisms. And so you take the measure, you push it forward to the group action. It's not the same as the original one, but after averaging, it is. So what you have to do is, again, you have to take the weight of G, mu of G, suppose that the group is countable for this thing. And it turns out that, you see, after pushing forward and taking the average, you get back the same measure. And so this is a property that you can study independently of the hidden measure property, but it is always true that a hidden measure, so note that it's always true that a hidden measure is harmonic. And sometimes there might be more than one harmonic measure depending on the group action. In the case of SL2R, for instance, there's only one harmonic measure, so it's not problematic. But for other groups, there could be more than one. And so what are the questions that we could ask? Well, we can ask many questions. So for instance, you can ask whether this measure is a nice measure, is a geometric measure. Is it a measure that comes from some geometric structure? So here the question is, can mu coincide with a geometric measure? So for instance, if G is PSL2R, right, then we can ask, can nu mu be equal to Lebesgue on the circle? In this case, you have this situation. You have this group of matrices, and you have this path that goes there. So this measure on the boundary has some nice property. It's, for instance, it's harmonic. But is it the same as, say, Lebesgue measure? Or even variation of this, can nu mu be absolutely continuous? With respect to, say, Lebesgue. So it turns out that this is basically never the case. So, but yeah, so somehow there are important conjectures that are related to this, and some of them are still open. So this is very much interesting area of research. Yes. Well, I'll say more. I mean, I can tell you, okay, I can tell you some results. So first of all, in some sense, so there's a theorem of Furstenberg that says, in some sense, they always can. So for any lattice gamma in PSL2R, there is mu on PSL2R such that mu is Lebesgue. So in fact, in that sense, it's true. However, the conjecture, this is called a singularity conjecture, is that for any finitely supported measure, mu on PSL2R not on mu, on a lattice gamma inside PSL2R. So lattice means it's discrete, it's a discrete subgroup, and the volume of the quotient is finite. Then, yeah, mu is never absolutely continuous with respect to Lebesgue. So so if we just take any measure, in fact, Furstenberg showed us that indeed this is how you pass when you want to prove superrigidity, is how you pass from the Lie group to the lattice. You want to say questions like, can an abstract group embed in a Lie group? Well, the way you say whether you can or not, sometimes proving that you can't, is by going through this step. You say, okay, you start with the Lie group, you go to the lattice, and you say, okay, there is a measure on the lattice that produces the same measure, and that's how you start. But on the other hand, if you want this mu to be finitely supported, so we just want some finite set of generators for your Fuchsian group to produce something even in the Lebesgue measure class, then the conjecture. So this I worked on it. I think we have the word record on this conjecture, but still not the whole conjecture. It's never absolutely continuous. Yes. Yeah. Yeah, that's right. Yes. So PSL2R. So if you take a Möbius transformation like this, so it's an isometry inside, but on the boundary, it also acts on the boundary as a homeomorphism. Yeah, so PSL2R can be thought of also as a homeomorphism. Oh, so yes. Yeah, it preserves the inside, and it also has to preserve the disk. Yeah. Yeah. So lattice, yeah. So this is a sort of going ahead of myself, but yeah, a lattice is a discrete subgroup, and such that the volume of the quotient is finite. So the most famous example is gamma equals SL or PSL to Z. In fact, for this group, the conjecture is known, but for other lattices, it's still no. Yes.
You mentioned that PSL2 are the formalized measures.
Yes.
Then doesn't the go down to change?
Yes. Try it.
Still open?
Try it. It's true. It's true. It is. It does. It is equivalent. Yes. Yes. Correct. Okay. So maybe let me finish the list of questions. So we have, I guess, at least two more. So again, the stereotypical example is this group acting on the disk, which is the example that we all have in mind when formulating this.
Mu.
Yes.
Mu in this example is looking over lattice and
Yeah.
In the theorem.
In both, yeah.
The first theorem.
Yes, yes.
Okay.
Yes. Yeah, you could also give up the lattice. Yeah, this is the other thing you can do. You can say, suppose I have a measure which is finitely supported on SL2R, but such that the group generated by the support is not a lattice. It's like dense. Then you can also do this. But if you want both at the same time, the conjecture is you can never do this. Okay, so the related question related to what Abdul was asking earlier is the geodesic tracking property. So we said that almost surely our walk will converge to a boundary point. And we know that the speed is positive. But what else can we say? Can we say that, so in some sense, again, the miracle here is that even though the original measure was somewhat symmetric, the walk sort of almost surely picks a direction. Of course, it can pick any direction. So, different draws of this coin tosses can give you other points on the boundary. But still, if you're given an infinite sequence of coin tosses, you will pick some direction. And now, what else? Can we make it more precise that you converge there? And so one thing you could do is whenever you have a walk, you can look at the geodesic in the space, and we can see after n steps. So geodesic is parameterized. So let's say, yeah. So let's say that gamma from 0 infinity to x is a geodesic ray. If gamma, the distance between gamma s and gamma t is s minus t for every s and t. And then, okay, gamma 0 is the space point. And so we assume that the speed is along the geodesic is 1. So now I run the walk for n steps. So Wn0 is here. And is there a point on the geodesic ray that is somewhat close to it? So this is gamma of t. And so, for instance, we say that this random walk has, for instance, a sublinear geodesic tracking property, which is the weakest form. If for almost every sample path, there exists a gamma, a geodesic ray, such that the distance between the n step of the walk and gamma divided by n goes to 0. So this is sublinear because we divide by n, it goes to 0. Then we can have more stronger properties, like logarithmic tracking means that if you put the log here and so forth. So this is one relatively weak condition that is still pretty useful. In fact, so what is interesting, you note that the law of large numbers, the classical law of large number, can be rephrased into geodesic tracking on R. It's kind of trivial, but let me let me show you what this means. So in that sense, you can see that really it is kind of a good notion, this geodesic tracking notion. Because, so you see, so we have x1 plus xn divided by n, which converges to L. So we can rewrite this by saying that x1 plus xn minus ln divided by n goes to 0. Right? But now note that gamma of t equals L, yeah, gamma of t equals t is geodesic. So geodesic ray in R. It's kind of trivial. It's the only, basically the only geodesic ray, you're just going to the right with the unit speed 1. Right? And so you can think of R as a metric space. So this guy here is a distance function. So you can say that law of large numbers is equivalent to say that the distance between x1 plus xn, which again, this is nothing but, remember that this is, in our notation, is really just W and O. I mean, this is the walk. So you could say that the distance between W and O, and gamma, this is gamma of ln divided by n, because the distance is just the absolute value. And this is nothing else than the geodesic time power. So again, it is somewhat trivial, but it's kind of interesting to see that you see, if you have this setting, you want to generalize to non-abelian groups, groups with some geometric action, well, it kind of makes quite a bit of sense to generalize it like this. Yes?
With the law of large numbers also become like a versus probability work versus almost early.
Yeah.
So is that just think you have important there? Do you usually have both when you have probability?
Yeah, I think so. Yeah, and again, you can do more sophisticated things where maybe you can replace this with log n, and sometimes it's also true in this hyperbolic situation. Yeah. Okay, so basically we're done. So maybe, yes, I can only say the last thing as a teaser, but I cannot give the definition. But I want to still say the word here. So once we have a group, once you have the group with this measure nu, so we have a space, we have a boundary. I'll have a group. And now this is well defined. And now the question is this a natural boundary for the random walk? And the notion of natural boundary again was invented by Furstenberg. So and it's called the Poisson or Poisson-Furstenberg boundary, or the Poisson boundary of G. So we will see later on that there is a notion of harmonic functions on the group, much like harmonic functions in the complex plane. And there is a Poisson representation formula. And the space where this is true, we call it the Poisson boundary. So in some sense, the question is is this boundary that we have from this geometric action the correct boundary from the point of view of the random walks and the point of view of harmonic functions. But yeah, I don't want to go deeper in this because this takes a much longer explanation. Okay, I think we're good. Are there any more questions?
Are two different, so are two different boundaries that are like natural from a random walk perspective like this? In which sense are they the same? Because I know one can be bigger than the other. But like, in which sense are they?
Well, the Poisson boundary is defined as a space, measurable space, in which the group acts, and with this measure. So the category in which one is working in this theory would be a space which is measured in G space, a space when there's a G action of the group by homeomorphisms, say. And up to measurable, so two spaces are the same, if there is a measurable G equivariant map that brings one measure to the other measure.
So this doesn't see cardinality.
So yeah, it's not extremely fine. Yeah, so you could have sometimes two different spaces with two kind of different boundaries, but if you neglect to measure zero set, for instance, you can. You don't see it. Yeah, I mean, this is much later on, but yes. Further questions or comments from the online audience? Okay, good. So if not, then I guess I'll see you on Thursday.